part 2 video for 6.4, the fundamental theorem of calculus, and this picks up with theorem 4, which is the evaluation part of the fundamental theorem of calculus. And again, this is a continuation of an exploration that we had in 6.3. So if f is continuous at every point of a to b, and if f is any antiderivative on f of a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. So that means you would find your antiderivative, you plug in the top bound, you plug in the bottom bound, and you subtract, and you're going to actually end up with the value of the integral. That leads us to example 5. We're going to evaluate using an antiderivative. So that's using that fundamental theorem of calculus, the evaluation part. So the antiderivative of x to the third power is 1/4 x to the fourth. We would actually, and the shortcut rules are going to be introduced in chapter 7, but for basic polynomials, you're going to add 1 to the exponent and then divide the entire function by the new exponent. So if I add 1 to 3, I'm going to get 4. And then I divide its coefficient, which is currently 1, by the 4. So that's how I get the 1/4 out in front. The antiderivative of the 1 then is merely x. And I'm evaluating that whole thing from -1 to 3. So I would plug in the 3 first. So that's 1/4 of 3 to the 4th plus 3 minus plugging in the -1. So 1/3 -1 to the 4th plus -1. Then we have some simplifying to do. 3 to the 4th power is 81 times, and I don't know why I changed that to a third from a fourth. I did that for both of them. See if I can fix that. Okay. So I have 81 over 4 plus 3. This is going to be a -1 to the 4th power is +1 times a fourth is a fourth minus 1. So this is 81 over 4 plus 3. 1/4 minus 1 is -3/4. The negative in front of that, though, makes it a +3/4. So I have 81/4 plus 3 plus 3/4, and that is going to give me 24. So 24 is going to be the area under the curve. Example 6, find the area of the region between the curve y equals 4 minus x squared, and x is in between 0 and 3, and the x-axis. Well, with this one, hopefully you can see there's a split at 2. So from 0 to 2, we are above the x-axis, and from 2 to 3, we are below the x-axis. Now this says find the area of the region between the curve and the x-axis. So this actually wants a total positive value. So we are actually going to split this up into 2 integrals. This is going to be the integral from 0 to 2 of 4 minus x squared dx, plus, because the second one is actually going to give us a negative value, and I want the total area there, I'm going to do the absolute value from 2 to 3 of 4 minus x squared dx. It can get tricky sometimes. Hopefully the book will explicitly state, or a problem will explicitly state if they want you to do the absolute value here. This one, because of the way it's worded, it doesn't just say find the area below the curve of the region. It says find the area between this and the x-axis. So that piece that would normally be negative, we're actually going to consider that a positive. So I got to do my antiderivatives. It's going to be 4x minus 1/3 x cubed. This one evaluated from 0 to 2. And then I would add to that the absolute value of 4x minus 1/3 x cubed this one evaluated from 2 to 3. So if I plug in my 2 here, I'm going to end up with 4 times 2 is 8. 2 cubed is 8 times a third, so 8 minus 8 thirds. 0, when I plug in 0, I'm just actually going to get 0 for both of those. And then I'm going to add to that what I get when I'm inside my absolute value. So that's going to be 12 minus 9. Because plugging in the 3, 4 times 3 is 12. 3 cubed is 27 times a third is 9. And then I'm subtracting from that. Plugging in the 2. So plug in the 2, I get 8. And then minus the 8 thirds, kind of like I did before there. So here, my 8 minus 8 thirds, that's going to give me 16 thirds. Over here, 12 minus 9 is 3. 8 minus 8 thirds, I know that's 16 thirds, so this is 3 minus 16 thirds. 3 minus 16 thirds is going to be negative 7 thirds. Well, when I take the absolute value, that's going to turn positive. So when I add those two together, I end up with 23 thirds as my total area between the curve and the x-axis. So here's how to find the total area analytically. Find the area between the graph of y equals f of x and the x-axis over the interval a to b analytically. You're going to partition your a to b with the zeros of f, integrate f over each subinterval, and then you're going to add the absolute values together. So if it says to find total area, that's a good indication that you do need to know to find the absolute values because your area has to be positive. And there are times whenever this is useful. We will see those, I believe, in chapter 7 and in chapter 8. For example, distance is one that comes to mind if you're integrating velocity to find distance. If you move in a positive velocity and in a negative velocity, you might be where you started from. But for example, if you're driving your car, you are going to be putting miles. I apologize for that. You're going to be putting miles on your car that are still going to tie into the wear and tear. So you want to make sure that you are still keeping in mind that wear and tear on the vehicle. So this brings us to example 7. Find the area of the region between the curve y equals x cosine of 2x and the x-axis over the interval -3 to 3 using fn int. So if we're going to do this using your fn int, I'm going to pull up, and instead of doing it, you can do the absolute value over the whole thing, or you can do the absolute value inside over the function. So you can do the absolute value of x cosine of 2x dx, and that would give you your value. So let's pull up our calculator and take a look at that. So math 9, -3 to 3 of absolute value is math over to NUM, hit enter. If you have one of the older calculators, you would see an ABS here. So that's x cosine 2x. I'm going to close that parenthesis and then get out of that absolute value. And my variable of integration is x. And this is going to be, it's basically going to take all the values that would be below the curve and flip them up above the curve. And it's going to give you a total value here as soon as it's done thinking. Moving a little bit slow here because of the absolute value. 5.425. So if you do this one correctly, 5.425 is what you should get for your solution. So that brings us to example 8. Graph of a continuous function with domain 0 to 8 is shown below. Let f be the function defined by h of x is equal to the integral from 1 to x f of t dt. So the first one, find h of 1. Well, it tells me up here what my h function is. So h of 1 would be the integral from 1 to 1 of f of t dt, and it doesn't even matter what f of t equals. Whenever you have the same bounds there, that value is going to be 0. Using what we know from 6.3, whenever we looked at all those values. So h of 1 is, well, that's the integration. And you can see here, I know we're right there. That's where I'm going to be starting from. Part B is h of 0 positive or negative. Well, h of 0 would be from 1 to 0 of f of t dt. So that's the negative from 0 to 1 of f of t dt. Well, from 0 to 1 is a positive value, so that would be the negative of a positive, which would then be a negative value. So you're basically thinking backwards. From 1 to 0 is positive, but since it's looking backwards, it would actually flip to be a negative value. I repeated the graph here just so you can see the rest of these questions. Part C, find the value of x for which h is a maximum. So again, remember, I'm starting at that 1. Where am I going to take on the biggest area? Well, it looks like the biggest area under the curve is going to be using this region and not getting into any of that negatives. So there would be a maximum at x equals 4. That's going to be the greatest value. Part D, find the value of x for which we have a minimum, where it takes on the most negative area. Looks like it is going to be at x equals 8. And then part E, find the x coordinates of all points of inflection of the graph of y equals h of x. So if you recall, that is the integral from 1 to x of f of t dt. So if I take the derivative of this, I'm just going to get f. So the derivative, if I do dy dx of that, I'm going to get f of x. And then if I take the derivative of this, I'm going to get f prime of x, which would be the slope. So anywhere my slope is equal to 0 is going to be where I have a point of inflection. So that happens at x equals 1, 3, and 6. So those would be all the places where we have points of inflection, again, by taking the second derivative. I know that there was quite a bit in this section, so please make sure you go back and watch this. You can reach out, find some other videos on the internet to help you with this. You can always reach out to me as well if you have any other questions. Please make sure you go back and rewatch the first video as well on the antiderivative properties, and hopefully we can continue working through our understanding of integrals.